I will be covering some topics related to DSP architectures. But before I get into the topic of DSP processors, it's important to understand the approach that I will be taking. There are many aspects to learning about the processor. You have to learn about its architecture, you have to learn about the instruction set. But in order to make sense out of all this and try to understand why the architecture is so designed, you first have to understand the basic signal processing operations that are there. For example, the dot product, matrix multiplication, the FFT, and so on. Right? Once you understand these, you understand what do we expect in a DSP processor, what sort of features you expect when you want to implement, for example, in a FIR filter. Right? Once you understand these, then the architecture, when we learn the architecture and when I present the details of the architecture to you, it will make much more sense. You have to correlate. It's not that the signal processing operations that I will be covering are new to you. I will be covering things like FIR filters, which I think you have done many times. But the idea in reviewing these topics is that you recollect the way in which these things have to be implemented. You can take an FFT, you think about how what implementation aspects alone. Right? Through that, we will try to bring out the architectural features that are desirable in a DSP. Okay? First of all, why do we use a DSP processor? I've heard of any DSP processor before. Yeah? These are special purpose processors. The first question that comes to mind is why do we use a DSP processor when we have processors like the Pentium, which operate very fast, right? They operate at several gigahertz, whereas most of these DSP processors operate at 200 or 400 megahertz at the most. Right? Which brings to question, why do we use special purpose processors when we have powerful processors with us? Right? We will bring out the importance, the reason why we use DSP processors. In fact, DSP processors are used in almost all handheld applications, mobile applications today. You open any PDA, you open a mobile, you will find the DSP processor embedded in it. Right? So we have to understand why we use a DSP processor. We will bring that out through typical operations, like for example the dot product, the convolution, filtering, FFT algorithm. The other important application that perhaps we do not have time to talk about is the Viterbi algorithm. And the DSP processors are primarily designed around these applications. As you might be knowing, there are benchmark applications, and DSP processors are tested against these benchmark applications. So it's important that they perform well. Right? So these are the typical applications typically we talk about. What I try to bring out through this lecture is the typical DSP operations and the indexing requirements that are there in these processors. The first and the simplest one would be the dot product. Right? The inner product between C and X. You are simply multiplying two vectors, point. Is it okay? You are taking the dot product of C and X. The C and X are n-length vectors. This sort of operation is very commonly performed. We will call this the multiply and accumulate operation because that is what is taking place. We are multiplying C1 with X1, C2 with X2, etc., and then adding all these things up. Right? It's a very basic DSP operation that is performed many times. You must first think what does a normal processor do? It will pick up C1, then it will put it in a register, it will pick up X1, put it in a register, multiply them, right? Put it in the accumulator, then it will go and pick up C2 and X2 and so on, right? But in order to do that, you must understand that there are certain indexing requirements. You are accessing C1 first, then the processor has to increment the pointer and make it point to C2. Right? Similarly, when you are accessing X1, next time you want to access X2, so the processor has to increment the pointer. So you can see that the basic operations are like this. You pick up C1 and then you increment the pointer. You pick up X1, you pick up its pointer, you increment its pointer. Then you multiply them and accumulate them and keep on doing this operation many times. In a typical processor, this will be very slow because you have multiple memory accesses which make it slow, and also the indexing operations that are required cannot be performed automatically. That means you have to increment pointer pointers separately in separate instructions. In DSP processors, these memory locations are accessed simultaneously. Is that okay? That means C1 is accessed at the same time as X1 is accessed. Is that okay? There are two separate memories. So the first thing that we understand is this. DSP processors utilize the Harvard or the modified Harvard architecture. This is somewhat different from the one Newman architecture that we use for general purpose processors. What's the basic difference? They have separate program and data memories. So from the program memory, you can pick up the coefficient C1, and from the data memory, which is separate, you pick up the X1. There are separate address buses and data buses for both program memory and data memory. So this is the fundamental difference between a DSP processor and a normal processor, general purpose processor. The sense that you can access two different memory locations at least at the same time. DSP processors like the C5510, the Texas Instruments, that I will be talking about later, allow the user to define sections of the memory as program memory and data memory. This makes it a modified Harvard architecture. Right? You can specify various locations. I think that is not important. The crossover path is allowed, and the 5510 allows 3 different quantities to be accessed simultaneously. Not 2 but 3. We will understand why this is so important. The other aspect that I brought out earlier was the indexing requirement for repeated operations for the multiple accumulate. I told you that one pointer has to be reserved for Ci and the other for Xi, and somebody has to increment the pointer for Ci and Xi so that in preparation for the next read operation that will take place. And at the end of it, you also have to remember that at the end you have to check if n operations have been completed. Somebody has to keep track of the number of multiple accumulators that have been done. Right? It means that this checking operation is also going to take time. You have to keep checking whether you have multiplied and accumulated n times. This in the C5510 or any other typical DSP processor, this is done using a single instruction, repeat, and then you make it repeat n times, and the next instruction would be a multiply, accumulate. These two instructions together completely perform the multiply, accumulate n times. Okay? So we find that these indexing requirements are all met by the processor. That means it automatically does all this indexing for C1, indexing for C2, Ci and Xi is all done automatically. And you will find that we have to do this multiply accumulate fairly often. Sometimes the number of quantities that are multiplied and accumulated can become very large. And we deal with fixed point processors for the most part, except high-end applications like military applications. Most of the time we end up using fixed point arithmetic. Then you have to worry about the chance of overflow. When you are multiplying large number of quantities and summing them, you have to be worried about overflow. So the processor has to take care to ensure that you can perform these multiply accumulates for large values of n without too much chance of overflow. So accumulator sizes, for example, will normally be very large. The C5510 is 16-bit processor, but it has an accumulator of size equal to 40. Primarily because when you multiply and accumulate, you don't want to risk the chance of overflow. Okay, now let us consider another application, convolution. And here I consider two finite length sequences h and x. These are vectors of length n and mx respectively. Is it okay? So when I convolve them, I should get sequences of length equal to n plus nx minus 1. Right? It's a different matter that convolutions of long length are implemented using FFTs. They are not implemented now as it is, but assume for the time being that we are dealing with convolutions of short length, and in which case you have to look into the convolution and try to understand the different ways in which you can implement the convolution. We will assume, of course, that h, the coefficients, which are normally the coefficients, are stored in program memory, and x, the array of numbers that you want to convolve with, are stored in the data memory. Okay. So that is the basic convolution expression. Is it okay? I have h of I x of n minus I, and I varies from 0 to n minus 1. And you can see that n varies from 0 to n plus nx minus 2. That means the convolution is of length equal to n plus nx minus 1. So to compute y of n, what are the quantities x that you would require? You require x from x of n to x of n minus capital N plus 1. That is the array, input array. You also require coefficients h of 0 to h of capital N minus 1. Okay. Now we need a pointer to access h. Is it not? So we have a separate pointer to access the h. We have a separate pointer to point to x. What you realize is that what are the, you need to access h0 to h of n minus 1. Is it right? Then each time you take h0, you multiply with x of n, h1 you multiply with x of n minus 1 and multiply it with it, right? But as soon as you finish with the computation of the output and you have computed y of n, you will realize that to compute y of n plus 1, again you require h0. You use h0, h1, h2, h of n minus 1, and to compute the next output again you require h of 0. So this sort of addressing, which we will be calling circular addressing, is present in the typical DSP process. You see that convolution requires or can greatly benefit from this sort of circular addressing in which the coefficient, when you have a pointer and you keep incrementing, it will keep incrementing within a boundary, then it goes back to the beginning when it exceeds the boundary. Similarly, when you are decrementing, it goes to the top of the buffer, and then when you decrement it further, it goes to the bottom of the buffer. These sort of buffers are called circular buffers, and you can see from this example that they are extremely useful for DSP. Okay, so what about the pointer for x of n? So look at the inputs that are used to compute y of n. What are the inputs x of n that I use? I use x of n to x of n minus capital N plus 1. That is to compute y of n. To compute y of n plus 1, which are the inputs that you will use? It will be x of n plus 1 to x of n minus capital N plus 2. Is it not? You will check this from the expression. You will find that you are using a new range, new values of the input. Actually, you are using one new input, x of n plus 1 is a new input that has just arrived. The new input, right? X of n plus 1 is a new input. And you will also realize that there is one output input x of n minus capital N plus 1, which is no longer used. That means that the type of pointer that you have for x of n has to be slightly different. Every time you of course need to increment x of n, but as soon as you finish capital N operations, you would like to go back not to x of n but to x of n plus 1, because that is what is required in order to compute the next output. Is it okay? So you will see that there are series of indexing requirements, so you actually need what to implement this sort of a simple operation, a very basic operation. You require two pointers, one for h, one for x. We said that the pointer for h has to increment, but it has to increment in a circular fashion, which means that when it reaches h of n minus 1, it should automatically go back to h0. The pointer for x of n, on the other hand, has to increment, but it should not be circular. So you will understand now that DSP processors are very different in the sense that they do the multiply accumulate. Right? It's a different thing that they do this multiply accumulate in a single clock cycle. Right? Not only they will not only do in a single clock cycle, you will find that all these indexing requirements are automatically taken care of. You have circular buffers to take care of the coefficient h. You have a certain sort of indexing advantage when you try to access x of n, in the sense that you can add to x of n or decrement from the pointer to x of n a certain value that I am going to come. So this again we are trying to bring out the importance of circular buffers, and also the fact that you sometimes need to increment and decrement a pointer not by 1 but by a larger amount. The pointer for x of n we had seen just now, it incremented by, it was at x of n minus capital N plus 1, and and it has to be incremented by n plus 1. So it will go to x of n plus 1. Right? The other application that I will deal with is filtering operation. So what is the difference between this and the convolution that I talked about? Here the input, I am talking about real-time filtering, which means that the input is of infinite length, right? And this is an important application. Normally you would find that these are implemented using FFTs. Normal filtering operations are implemented using FFTs. Nevertheless, if the filter is of short length, I suppose this sort of normal filtering operation would be fine. And I think this requirement for filtering in DSP is very, very vast. In fact, you have to implement low pass filters, high pass filters, band pass and band stop filters. Many applications. Almost all applications require some sort of filtering or the other. And for that reason, ability to implement filtering in a computationally efficient fashion is very, very important. The difference between convolution and filtering, as I was saying, was that here the input comes one at a time. You don't have a fixed array of length equal to n. Right? So, what are the things that we can say? Look at the basic expression. Of course, the same as that of convolution. There is no difference. The difference, of course, is in the fact that at x of n, you can only store capital N values. Is it fine? How many values of input x of n do you really need for this computation? Capital N. Right? So, at any given point of time, you can store only capital N values. Why is this so important? In practical applications, the order of the filter N can be sometimes very, very large. Depends on the application. If it is 64 or 128, you cannot afford to store large values of the input x of n. Right? You can see that the filter itself requires only capital N values of the input to be stored at any given point of time. At any given point of time. Then the inputs x of n that are required at different instants of time will be different. Are you able to see that? The first time, for example, if I want to compute y of n, I require x of n to x of n minus capital N plus 1. To compute x of n plus 1, I would require x of n plus 1 to x of n minus capital N plus 2. So every time I require a new set of inputs. That is the basic difference. So in basic filtering operation, you will find that this requirement has to be met. And then these filters and how they are implemented, I will be discussing very soon. Right? But you see the difference between convolution and filtering. Right? So before I proceed ahead, I think all of you are familiar, but anyway, h of e power j omega, which is the Fourier transform, I think I'll record a negative sign there, e power j omega n, that is referred to as the frequency response of the filter. The h of e power j omega will be complex, both so magnitude and phase are both plotted. I think these things you are all very familiar with. In FR, filters are preferred for their guaranteed stability because with finite word length effects. This is important when I implement in practice because you do not, in spite of finite word length effects, filters will always be stable. And in adaptive systems where h of n, the coefficients can keep constantly changing, but FR don't have to worry about stability. FR filters, however, require a large number of coefficients. Is it not? In this you would have learned in DSP. The number of coefficients required to implement any given typical response would be larger in the case of FIR. So you have to do more amount of arithmetic in implementation to get the same frequency response. But nevertheless, FIR filters are used in most applications because of the stability of both, as I mentioned, but also because they can be designed to give you a linear phase. Right? You see, for examples like speech and other applications like that, where the phase is very important. You will find that whenever IR filters are used, phase compensation is used. All this makes it very complicated. With FIR filters, you don't have to worry about phase. Okay? I think we will discuss IR filters also because I think together we can discuss the implementation aspects. Right? So let us look at IR filters. These are infinite impulse response filters, IIR. As you can see, these are feedback type of filters. So the output at any given point of time is the weighted sum of the inputs and also some weighted sum of the past previous outputs. Right? So what do you notice? You notice that you require one index for H, one index for X, one index for G, and one index for Y. So the indexing requirements for IR filter, as you can see, is slightly different. You require more number of pointers. But nevertheless, the basic operation that is performed for the input and the output are really the same. Right? And that I would like to bring out. I think as you are familiar, this is stability is an issue for causal type of filters which we want to implement. Okay, now let's get back to our topic proper, the indexing issues in IR filtering. So whatever I say about FR filtering will be equally valid also for IR filtering, because the basic operations that you need to perform are the same. Okay, now let's consider an array of size equal to capital N. And I think this is what I was saying earlier, that y of n requires x of n to x of n minus capital N plus 1, but y of n plus 1 requires x of n plus 1 to x of n minus capital N plus 2. The important point is that x of n minus capital N plus 1 is no longer required. That means you should not store it, you should destroy it. Right? Because the array that you have cannot be of size greater than n. Okay, that is one thing. Then how are you going to store these quantities? You will store them in an array of, you are going to have an array of numbers starting from x of n and maybe going down to x of n minus capital N plus 1. Next time what happens? You have performed the filtering operation, you have computed y of n. You have to prepare for the new input x of n plus 1. I think this you are familiar with, right? When you perform a filtering operation, you have to do this multiply, accumulate, compute and output before the new sample arrives. For example, in the case of speech, the new sample arrives every 125 microseconds. So within this 125 microseconds, you should have performed all your multiply accumulates and you should be ready. What are the things that you need to do for you to be ready? You must understand that where you store x of n plus 1. You have an array starting with x of n and ending with x of n minus capital N plus 1. And you don't require the last one, but you require to store x of n plus 1 in the top of the array. How will you do that? Right? One option would be slightly more difficult perhaps, but it turns out that this is what the processor performs. It performs a move operation. It performs a move operation. So what it does is something like this, very ingenious, and the way in which this is solved. Whenever it reads some one memory location, it copies the same thing into the next memory location. So obviously you can't start a filtering operation from x of n, then you will be destroying data before you are using it. What is done is like this, you start from x of n minus capital N plus 1, multiply it with h of n, then that is copied to the next higher location which you are not bothered about. Then you start with h of n minus 1, h of n minus 2 and multiply it with the next input and keep on doing this. That is copied downwards. So when you reach x of n would be copied to x of n minus 1th location. So every entire array of inputs has moved downwards. Is it okay? So this operation of move, if it's a typical, it's a non-DSP processor, you have to perform this move on your own. This can be extremely time consuming. Once you perform your filtering, you have to perform capital N moves and move the entire array downwards to create space for x of n plus 1. Right? But in a DSP processor, while it is reading, it copies to the next location and therefore it becomes very, very efficient. Right? This is called filtering with a move. I will show you later the 5510 processor will do this. Is this okay? There is one more approach, equally good, that can be used. The option is like this. You have an array of all the inputs of size equal to capital N. I already told you that the coefficients we can use a circular buffer. It makes best sense to use a circular buffer. But for the input also we can consider using a circular buffer. Is it not? I store numbers from x of n to x of n minus capital N plus 1. Whenever the new input arrives, I can put it in different locations depending upon, I can store it in the place of x of n minus capital N plus 1, which I no longer require. Then I need a pointer that moves in a circular fashion. And I will see that if I have a circular type of buffer and allow the pointer to vary in a circular fashion, I can always store the new input not at a fixed location like I was doing earlier, but at different locations. Right? See, as you can see, when I want to compute y of n, in preparation for y of n plus 1, I would store x of n plus 1 in, I will store it in the location where x of n minus capital N plus 1 was stored. Next time we will store it in the previous location. So the place where you store the new input can keep varying and vary in a circular fashion. This is also an ingenious way of solving the indexing requirement. Right? So because we do have circular buffers in typical DSP processors, you can use either of these approaches to solve the problem.
So the index would move no, rather than the input?
The index would move, yes. The place where you store.
Only the index will be moving, not the data.
No. You're going to implement you're going to use the circular buffer for accessing the inputs, and you have a pointer that moves in a circular fashion that helps you to store the input.
It will point every time to the new input.
Yeah.
Start with the new input.
The input that you no longer require now, in that place will store the input that is just arrived. It does not matter because the pointers are on circular. You'll always read this capital and capital N values. Yeah? In the earlier case, in the option 1, we were always storing x of the new input in exactly the same location at the top of the array. Right? Here we have to do it in a circular fashion.
So then addressing is also not after one memory location to one memory location then for reading the data?
Why?
Addressing.
That does not matter because it is in a circular type of buffer. Right? You're going to start at one particular location and keep moving upwards and upwards. At the last sample, you will always read, for example, when you are accessing H0, you will always read the new sample that is just arrived. Because the pointer is pointing to that location. So when you decrement your pointer, you are reading the previous location in the input and so on. It does not matter where you are currently, you will always read n samples, n values. Right? So it doesn't make a difference. As long as you are moving in a circular fashion, you can check out with an example if you like. Okay, the other important aspect when it comes to filters is the notion of generalized linear phase FAR filters and how they are implemented. I think all of you would have covered this in DSP. One of the things that we design of FAR filters, and the reason why we use them so often, is that they can be designed to have a linear phase. Right? The notion of a linear phase will come out like this. I think again I have installed the sine and the for geometry n. But if you look at the Fourier transform and look at the phase of the Fourier transform, you will find that we want it to be a linear function of the frequency. Is it okay? I think this you would have covered in DSP. This would be very useful. What this ensures is that every signal, a signal of any frequency, gets delayed by exactly the same amount, let us say d. In order for that to be possible, it is important that the phase response be a linear function of frequency. Right? This you will learn, might have learned in DSP. But of course, the function that I have written, strangely enough, is not a linear function. It is alpha omega plus b plus beta. It is not a linear function, strictly speaking, but it does not matter because the derivative of the phase, that is, the derivative is still a linear function, right? You take the derivative, the beta vanishes, so it is fine. So you will find that that's why we call it the generalized linear phase. If it is a linear phase, we would require that the phase phi of u per omega be a function of scaled version of the frequency. Okay, that we will learn maybe in the DSP course. But what is of importance to us is like this. Whenever I put restrictions in the frequency domain, I always have corresponding restrictions in the time domain. Is that? So for example, if I require the filter to be real, coefficients to be real, the frequency domain there is a conjugate symmetry. Right? So for example, if I want the Fourier transform to be real, then we conjugate the filter coefficients into conjugate symmetry. Right? Similarly, if I place a restriction on the phase of the Fourier transform of the impulse response, then automatically you will find, you can show that there are restrictions on the locations of the zeros of the impulse response. The zeros of the impulse response will only occur in conjugate reciprocal pairs. You will find that if there is a 0 at Z0, there has to be a 0 at 1 by Z0 conjugate. In addition to that, the implication for us is like this. The impulse response will be either purely symmetric or antisymmetric. Why is that so important for us? Because when we implement, it will be okay. Let us look at this typical. Just bring it out for this. These are the 4 types of generalized linear phase FIR filters you will find in any standard book on DSP. Now look at the first one. How do you implement this? This is the impulse response, right? H0 to H8. Right? It is an odd length filter. The n is equal to it. Odd length filter. If you look at it, you have to take H0 and multiply it with x of n. Right? And H0 happens to be the same as H8. Is it correct? So what should you multiply H8 with? You should multiply H8 with x of n minus 8. But H8 is equal to H0. So what is the normal? What comes immediately to your mind? Because you have to take H0 and multiply it with x of n, and H8 is equal to H0 and multiply with x of n minus 8. The logical thing to do is to first add x of n and x of n minus 8 and then multiply it with. Well, is it not? It is much more sensible to do that, because I hope you are able to see it. We are to take this, maybe I will show you the expression to make it clear. Go back to look at that expression. I have H0 multiplying x of n, and if capital N is equal to 8, I have h of capital N. I think I have assumed it to 9. The way how I represent it is slightly different. But anyway, if I take h of 8, I have to multiply it with x of n minus 8. If H0 and H8 are the same, that would mean that I can add x of n and x of n minus 8 and multiply it with H0. Why is this so important? Because multiplications are very power hungry. If I have 2 different multiply accumulate units, it does not, that does not mean that we can use them together. It is not smart to do it because of the fact that you will be wasting power. Many of these DSP applications are very power sensitive. They are handheld devices, PDAs, mobiles, in which power is at a premium, that you are running on batteries. So for that reason, you want to utilize as less power as possible. We will later see the DSP architecture. They go to very great lengths to ensure that power is saved. Right? So one of the things that you will see here is that if you minimize the number of times the Mach unit is used, you will save power. So it makes much more sense then to take x of n. In the first case, let us go back to the first example. We take h of 0 and multiply it with x of n. I take h of 8 and multiply it with x of n minus 8. But instead of doing that, I will take h0, I will take x of n and x of n minus 8, add them both up, and then I will multiply with h0. Then I will take x of n minus 1 and x of n minus 7, add them and multiply with h of 1. This is a much smarter way of doing things. What will be the number of multiply accumulates that you really have to do? Number of multiplications you have to do in this case. The length of the filter is n. You will be roughly doing around n by 2 multiplications. That means a filter of order equal to n, depending of course on whether it's even or odd, and the point of symmetry. When n is very large, approximately we will be doing n by 2 multiplications. Right? So it means that a filter, a generalized linear phase filter, can be implemented much more efficiently if we have the ability to first add 2 numbers, that means, and then multiply. This sort of instruction is provided in the C5510. This is called the FRRS add. That is what it does. It's an FIR instruction, but it adds 2 different quantities. within the same array, takes two different quantities, adds them, and then multiplies them together. Right? Of course, it saves you time because you are doing n by 2 computations only. In addition to time, what is important is that it also saves you power because you are not actually. Is it okay? Every time you have a bus access, you are wasting power. Every time you use a multiply accumulate unit, you are wasting power. So this way, it is much better. Right? You are using using the multiply accumulate unit less number of times, and therefore it saves you power. The FIRS add will implement a symmetric filter. The FIRS sub will implement an asymmetric, anti-symmetric. If you want to implement complex filters, what would be different? How would it be different from this? I don't think the indexing requirements will change too much, except that it will require more pointers. When you have complex inputs and complex coefficients, you have to store the real numbers and the imaginary parts of inputs and real and imaginary parts of the coefficients separately. You automatically require more pointers. And every multiplication, complex multiplication, you can break it up into 4 real multiplications. Is it correct? Which means that it would be nice if there are multiple multiply accumulate units in the processor. Is it correct? If I have more multiply accumulate units, I can implement this complex filter much more efficiently, faster. Right? So the C5510, for example, has 2 multiply accumulate units, which means that if I have a filter of order equal to n, I should be able to implement it in n by 2 cycles. Because the filter of order n requires n multiply accumulates, and there are 2 multiply accumulate units. Right? For example, if I want to implement a complex filter, it should become much more efficient if I have more number of packs. The more the number of multiply accumulate units, the better it is for us. I next talk about the matrix products. I will not dwell too much on this, but maybe I will just give you an overview. The matrix product involves a series of dot products. Is it not? You multiply rows with columns and so on. But I want to think for a moment about how we are going to store these numbers. You decide that I will store the elements row wise or column wise. Right? Let us say I decide to store them row wise. How will you start reading those numbers? You will read the first matrix row wise and watch how should the pointer increment. By 1, right? Because you stored them row wise, so you have to increment by 1. But what about the second, the column? You have to multiply a row with a column. What about the column? The column has to be incremented by, not by 1, but by a larger number, right? So that is the point I am trying to make. You have to multiply n cross n matrix with an n cross r matrix. Every time I access the second matrix elements, in order to do the dot product, I have to increment the pointer not by 1 but by value equal to n. Value equal to r. Yeah, number of rows, number of columns that are present, right? So what it means, this brings out a new requirement for indexing, is that I should be able to increment any pointer by 1, increment or decrement by 1, that's anyway present, but I should be able to increment it by a number that is larger than 1 every time. That would be desirable. So the 5510, for example, provides for such increments. That means you can increment the pointer by a number that is stored in a particular register.
The storage will be a static or dynamic memory allocation in that case. It will be a static memory allocation or a dynamic. Like we are using arrays or.
I am assuming that the entire matrix is stored in row wise. Both the matrices are stored.
So I am talking in the programming point, like if we are implementing it in the C language. So that will be a static.
I am not interested in C language. I am right now talking about the processor and the way it implements. Here I think we are dealing with numbers that are stored in the memory. My focus is on how we are going to pick up these numbers and what requirements we have when you do so. Right? The point I am trying to make out is that there is a need to increment the pointer not by 1 but by a larger number. Right? I will come to the point. The fast Fourier transforms, I don't know how many of you have covered. I think many of you would at least have covered in DSP at some time. The idea here is not to cover DSP, the fast Fourier transforms itself, but to bring out for you the indexing requirements that are present there. Well, I think most of you would have done the radix 2 algorithms because they're very, very popular. I will just go through the basic ideas of the FFT. The FFT is implemented discrete Fourier transform. That means we take finite number of points in the time domain and bring it to the frequency domain. Get equally spaced samples in the unit circle. Fourier transform in the unit circle. This you are all comfortable with. I am denoting the DFT by capital X of K, and these Wn power Nk, these are called the twiddle factors. These are complex quantities that you need to multiply x of n with, right? And most of the cases x of n will also be complex. This is rather strange, but in radix 2 FFT, if you have an FFT of a very large size, FFT is not FFT of the real number, the real vector, it makes much more sense to convert it into a half-length complex quantity vector and then take its FFT. Right? For that reason, most of the time we deal with x of n that will be complex. That means the input x of n is complex. The coefficients which are called the twiddle factors will also be complex. So that changes a few things. You require multiple arrays for storing the real here to access the real part and the imaginary part. Okay. I think the basic idea of a DFT, I think you are comfortable with. This requires n square complex multiplications, not b. Is that correct? To perform this for all values of k, p equal to 0 to n minus 1, you require n square complex multiplications. The basic idea of a DFT is to try to exploit the fact that the computation is square of the size of the unit. Because it is proportional to the square, if you can somehow split it into two parts such that then the computation will become n by 2 square, and n by 2 whole square can be much smaller than n square. And so what I have shown here is that I have separated the sequence into the even part and the odd part, which is one type of FFT, that is 2 FFT, and I written it x of k, the DFT of size equal to n, as the sum of two DFTs of size equal to n by 2. Right? And these Wn power k are factors that will come in, that they will show in the figure. I will show you. But you will find that you have to take two DFTs, you have to multiply with Wn power k, right? And this Wn power k would involve extra computation of n by 2. So you can keep doing this repeatedly. My point here is not the FFT algorithm itself, but the basic computational requirements. But nevertheless, you can show that the amount of computation that is required becomes proportional to the log, right? Let's say n log n, which can be much smaller than n square. And we have to worry about how we are going to access these coefficients Wn. Let's look at it. This is the basic computational unit. This is the basic butterfly. Okay? The FFT, I will be showing you the figure, involves basic computation with the signal flow graph. You have to take two numbers and you have to take the second number, multiply it with Wn power n. Is it okay? This I am going to call the twiddle factors. I am going to multiply it and then I have to add it with the first number. To compute the second number output, I have to take the first input and then I have to take the second input, multiply Wn power and then subtract it from the first one. So these are the two things I have to do. This is a basic butterfly. It's called a butterfly because it looks like a butterfly, but the amount of computation that is required is one complex multiplication to compute these two outputs. So you take two inputs and you produce two outputs. Right? So this is a basic computational unit. Now I will show you the basic FFT diagram itself. Of course, I am not going through all the aspects of the FFT, but this is a similar to graph of the FFT. This is an example of an 8-length FFT. You will notice that the outputs are x0 to x of 7, but you will notice that the input is not in the it's a different type of order. Right? So what are the things that you need to do to implement the first stage? You have to take x of 0. It's a different matter that their numbers are all complex. That's a complication you can deal with by storing in two different arrays or storing them sequentially, real, imaginary, and so on. Assuming that I can do that, I have to access x0 first, then I have to jump to next number I need to access is the one required to implement the first butterfly, which will be x4. So I have to take x0 and x4 and to perform the basic computation. But how do I know from x0 I have to access x4? The next number that I will access will be x2. So this is a strange type of indexing which is called the bit reversed addressing. So what happens is that the last 3 bits of the address have to be flipped. The carry is propagated in the wrong direction, rightwards. I think this you are possibly comfortable with anyway, but I mean, you look at the last 3 bits, since you start with 0, 0, 0, then next time by normal order you go to 0, 0, 1. But instead what you do is this. Okay? Then you keep adding 1 here. When you add 1, this becomes, right? So this becomes 0, carry 1, 0, and carry 1, 0. Carry is propagated in the wrong direction. So this is the 0, this is 4, this is 2. That will be 1, 1, 0, that is 0. Right? So you can access in the right direction if somehow the pointers can increment not in the normal order but in the bit reverse order where the carry is propagated in the wrong direction. Right? In the first stage, you will see that the carry has to be, the last 3 bits have to be, you have to worry about the last 3 bits. Right? Then you look at, if that is okay with everybody, then I can look at the requirement in the second stage. In the second stage, what is the sequence of numbers that you have to access? You have to access, you must understand that you read up x0, x4 and you are storing the output in the same memory locations. That is the concept in FFT, that you don't utilize extra memory, right? So, if you implement the first butterfly of the second stage, what are the sequence of numbers that you are accessing? First you will access the memory location x0, second time, then you have to access x2. That means the bits are getting reversed, but only in the last 2 bits are getting reversed. Bit reversal is still taking place. It's like this. I'm adding 2, then you access 0, 1, and so on. The only last 2 bits are getting reversed. That means that first you access x0, then you access x2, right? Then you access then you access x4 and then you access x6. The last 2 bits are getting reversed, right? The last stage, the last 1 bit will get reversed. So this bit reverse addressing is provided for by typical DSP processor. The reason is that FFT is a very important benchmark for a DSP processor. We should be able to implement it very efficiently. The fact that sometimes the input is in bit reverse order, sometimes the output is in bit reverse order, that depends on the implementation of the FFT. But you need to have the ability to access inputs in bit reverse order. And this has to be done in hardware. That means every time you access a memory location and say increment, it should be incremented in bit reverse fashion. And the number of bits that you have to take care also has to depend on the stage, and that should be variable. The other important point is that the twiddle factors, W and 0. How do you think the W and 0s should be stored? How many W and 0s, the twiddle factors, are we storing in an 8 and a 50? We are storing W and 0, W and 1, W and 2 and W and 3. Right? The rest are not required because of symmetry. Right? We have exploited symmetry already. Now look at the first stage. The only quantity that you are accessing would be W and 0. The second stage you are accessing W and 0 and then W and 2. The third stage you are accessing all the 4 quantities. This is a nice case for circular buffers. You have a circular buffer of size equal to, let's say for the real part, let us say, size equal to 4. In the first case, you increment the pointer by 4. Does it make sense? I store the twiddle factors, the real part for example, and I have a circular buffer of size equal to 4 and I am incrementing by 4. Then what happens? Every time I am at W and 0, I am incrementing by 4 and going back to W and 0. The second stage, when I am implementing the second stage, I am having a 4 length array of course. but I'm going to increment the circular buffer by 2. So I'm at W and 0, I'm going to W and 2. Then I'm going, right? Then again I'm going back to the right? The last stage I increment only by 1. But you can immediately see that the student factors, to implement these student factors, to access them, it is very nice to use a circular purpose. This is one other example where circular purpose can be very useful. So there are two things: the inputs. When you access the inputs, you need to access them in a bit reverse order often, and in order to do that, you must have bit reverse addressing mode available with you, and that is provided for. You will find the circular purpose are also provided for in most DSP processors. Right? These are the architectural features I thought I should bring up. So this would be the summary. There is one other application that I did not talk about much, which is extremely important. Typically algorithm. It requires slightly different type of computations. Computation of distances, comparing distances, and so on, for which the processor has provided instructions. The features are very suitable for that, but I did not talk about the replication. So what the summary would be that DSP processors require very specialized functions to be implemented with very specific indexing and other requirements. That's what we have seen not many examples, right? And the DSP processors are designed to take care of these and provide for these. And in order to program very well, you have to understand the architecture very well. Is it not? And to understand the architecture, you must understand why that feature is provided for in the first place. So it's important to go through the DSP operations. So since we have gone through these DSP operations, we will now go back and look at the architectural features of the processor, and then I hope you will make sense of most of the features that are present. Is it fine? If you have any questions, you can ask. Otherwise, you can have a short break.
So I did not get the bit reversal.
Okay, maybe we'll cover it later. Bit reversal is just that the carries propagate in the different manner. I'll take the first stage. 0, 0, 0. So normally you would add 1 here. And what we are doing now is like this. Adding 1 here and getting 4. Next time you add 1 here and propagate the carry not this way but this way. Right? So this becomes 0, 1, 0. So 0, 4, 2. So you add 1 here.